Hey kids, this is Dr. Rones with your lesson for Objective 20. We are going to learn how to convert numbers into scientific notation and also how to take numbers from scientific notation and put them back into standard form. This is a really important lesson, so I hope that this is clear for you and helpful. Of course, it's not going to probably be the best lesson known to man, but we're going to sure try and make sure you learn this stuff. And if you have follow-up questions, you know that I'm always happy to follow up with you and answer any of those questions. So, as we learned previously, scientific notation is a form of writing a number that is typically extremely large or extremely small. So this is a semi-large number, hundreds, thousands, millions, 4,120,000. And so we could write this relatively large number in scientific notation if we want, if that suits our purposes better. Now there's a couple of rules in doing this. First of all, there will always be only one digit before the decimal, between 1 and 9. So in this case, our first number is going to be 4, and then a decimal. And then after that, we are going to continue writing all of our other non-zero numbers. So after the 4 is 1, and then 2, but we're going to wait. We are going to drop all of the zeros at the end. We're going to take those into consideration in a future step, but not quite yet. Now, we are going to take this base of 4.12, or 4 and 1200ths, and we are going to multiply that by a base of 10 with some exponent so that it's equal. So another way of thinking about what we're doing this is 4.12 times 10 to what power gives us 4,120,000. So over here for scientific notation, we put the decimal between the 4 and the 1. So that means we have to move this decimal 1, 2, 3, 4, 5, 6 place values to the right. We need to multiply it by 6 powers of 10. Another way to say that is if I multiply 4.12 times 1,000,000, that's 6 zeros, I would get 4,120,000. Okay? Now we're not actually going to multiply that out because it would take forever. Okay, you will notice here that I used a multiplication X, not the dot. So up to this point we have been using the dot, and I'm not being a hypocrite here. This is just one of those places where it is the right thing. It is the most mature form to use the multiplication X. So when you are writing numbers in scientific notation, which is numbers like this, that X is not going to be confused with a variable. You'll be fine. So another form that you will see these in is numbers in scientific notation can also be written with an E instead of that times 10. So for example, this one up here, 4.12 times 10 to the 6th, especially in technology, you might see instead 4.12 E6. And so that means times 10 to the 6th power. Okay? All right, all of those mean the same thing. So in our notes moving down, you are going to have standard form, or like the normal way, down the left, and scientific notation down the right. And so we are going to practice converting from one side to the other. We'll learn the ins and outs of all those subtle little rules, and so by participating, you will have kind of a guide on what to do for all of these different situations. So remember, the rule is to start by writing the first digit, then a decimal, and then all of the other numbers until you start getting to zeros. So we're going to stop because we don't need all of these zeros. That's kind of the point of scientific notation, is to eliminate having to write all of those zeros. And then times 10. So we put our decimal between 8 and 9. So between 8 and 9. So now we need to see how many powers of 10 we need to multiply by to get hundreds, thousands, millions, billions, 8,973,000,000 even. So 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9th power. Now, when I say to drop the zeros, I do not mean the zeros between two non-zero numbers. So this 0 is important because it's kind of holding a power of 10 position here. So we keep that. It's the zeros at the end that we're going to drop here. And it's not that they go away, it's just that we don't write them here because we kind of account for them with our exponent. So there's the point here. And now to get to the end, I'm going to go 3, 6, 9, 12 places times 10 to the 12th power. All right, try that next one. Did you write 8.9? That's the first digit, then the decimal, then a non-zero number, times 10 to the 6th. Because that's where the decimal is, you need to go 1, 2, 3, 4, 5, 6 places to the right. Now, one thing that you will notice, all of these positive exponents are large numbers. Now we're going to start talking about decimals, numbers that are less than 1. So when you do this, you'll still follow a similar procedure. It's just kind of like it's backwards. So write the first non-zero digit, which we have to pass the decimal and go clear over here, then the decimal, and then 8-1, right? Okay. Times 10, and because this is a decimal, I know that this is going to be a negative exponent. Now, the decimal over here was right about there, right? Not right about there. It was right there, right? So we need to count how many multiples of 10 or how many place values I need to move to the left to get to that decimal point. So 1, 2, 3, 4, 5 places. Let's try another one in case I lost you. So first non-zero number is 7, followed by what? 612 times 10. Positive or negative? Negative because it's a decimal. And how many powers of 10? 1, 2, 3, 4, 5, 6. Great. Try the next one on your own. Did you write 2.01? I hope you did. You should keep this 0. It's all the ones that precede it that you are going to drop. Times 10 to the, there's where we put the decimal between the 2 and the 0. 1, 2, 3 place values away from the number in standard form. And because it's a decimal, I know it's a negative exponent. Okay, that's how to go from standard form into scientific notation. And we can do the opposite to take numbers that are in scientific notation and put them into standard form. So here I have 4.602 times 10 to the 7th. So I'm going to write that same 4.602, but I'm not going to put the decimal there. So I'm just writing the digits, 4602. And this says that to get the number in standard form, I need to multiply this base by 7 powers of 10. Or another way to say that is I need to move my decimal place 7 places to the right from where the decimal was in scientific notation. So it was here between the 4 and the 6, and I needed to move 7 places to the right. 1, 2, 3. What do I do now? I need more stuff here. Well, what do I use for a placeholder? Were you thinking of 0? Yeah. So 1, 2, 3, 4, 5, 6, 7. In case that was confusing to you, I'll maybe use some color here. So this is where the decimal was in scientific notation. This, see here? And we have to move 7 places. So 1, 2, 3, and then 4, 5, 6, 7. And then once you're done with that, you should go back and add commas after everything, 3 numbers, moving from the right to the left. All right, let's try another one. 2.34 times 10 to the 15th. So we'll start by running 2, 3, 4. And now I need to move 15 place values to the right. So this is where the decimal was. So 1, 2. Uh-oh, I need to get to 15. Means I need 13 zeros. As you're writing those all in, you should be glad that, we know how to use scientific notation and we don't have to do that. So then, start from the right and add some commas after or between every group of 3. Pardon me. Let's see what this number is called, by the way. Hundreds, thousands, millions, billions, trillions. This is called a quadrillion. This is 2 quadrillion, 340 trillion. I did not make that up. That's actually like a thing. Okay, so this time I am going to convert a number in scientific notation with a negative exponent into standard form. So that means this time I'm going to move my decimal point to the left because I want a very small number because this is a negative exponent. It should be less than 1. So I'm going to actually start to the right here to give myself some space. So these are my digits, 1 and 7. This is where the decimal place was, and I need to move back 6 multiples of 10. So 1, 2, 3, 4, 5, 6. Let's count it out again. 1, 2, 3, 4, 5, 6. That's where you plop the decimal point, and because we are great math students, we always put a placeholder 0 in front. Please note, though, that that placeholder 0 in the front is not included in this exponent, right? Okay. Try that next one without me. Did you write 65042? That's where the decimal is. I need to move 11 place values to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do you have to write all of those zeros? Yes, you do have to write all those zeros. You will not die. Double count just to be sure. 1, 3, 4, 5, 6, 7, 8, 9, 10. Yep. Plop down your decimal and your 0. Do decimals get commas? No, they don't. Do not put decimals in your commas, please. Okay? All right, moving on. Now, we have said up to this point that you write the first digit, and then the decimal, and then all the other non-zero digits. But this is all zeros. So when this happens, we will write a single 0 to say, after that 5, it was only zeros. Times 10 to what power? 1, 2, 3, 4, 5, 6, to the power of 6. Same as if there are no zeros after in a decimal. 7.0 times 10. Because this is a decimal, I know it'll be a negative exponent. And I'm going to move 1, 2, 3, 4, 5, 6, 7 place values to the left. Okay. Well, here's a tricky one. This says the first non-zero, oh, there's the thing, 0893. Well, it's the same thing. First of all, would we typically write this in scientific notation if the standard form is understandable? Probably not, but having good number sense is really important, right? So, because it's scientific notation, times 10, but how many places do I have to move my decimal? No places, right? So the number for nothing is 0. Why does that make sense? 10 to the power of 0 is 1. And anything times 1 is itself. So that's why that makes sense. Okay, so as we said at the top, this E means the same thing as times 10. So this means the same thing as times 10 to the 6th. Or this means 6.982 times 10 to the negative 7th. Please write in those two numbers, and I'll catch up with you in just a second. Okay, and so we have the 5, 3, and 2, 6 places to the right, because I want to make this number bigger because this is a positive exponent. So 1, 2, 3, 4, 5, 6. Sorry to keep starting and stopping the recording. I keep coughing. All right, 6, 9, 8, 2. And now I need to move 7 place values to the 7, or to the left. 1, 2, 3, 4, 5, 6, 7, and 0. No commas here, but I should have put commas up here. All right, that's fine. Pardon me. Of course I would start coughing when I need to record a video. Okay, so knowing procedures is great, but it's not helpful if we don't understand why it actually works. So let's do a couple examples of why does this work. Well, we said previously that 5.987 times 10 to the 5th is the same as what? There's where the decimal is. I need to move 5 places to the right. 1, 2, 3, 4, 5. Put the decimals in. So 5.987 times 10 to the 5th is the same as 598,700. But why? Well, let's study this part here to see what it really means. So that means 5.987 times, what is 10 to the 5th? Yeah. 10 times 10 times 10 times 10 times 10. Okay, let's simplify that. Okay, 10 times 10 is 100. 10 100s is 1,000. 10 thousands is 10,000, right? And 10 of those is 100,000. Or another way to do it is 1, 2, 3, 4, 5 multiples of 10. 1, 2, 3, 4, 5 zeros. And then if I multiply 5.987 times 100,000, either using a calculator. Well, look, here are, remember when you learned how to multiply the long way, right? As long as this was a 0, we could just do a placeholder and go to the next place value until we get to a 1. 7 times 1, 8 times 1, 9 times 1, 5 times 1, and I need to move 1, 2, 3 place values. So it comes out to be, here we go, 598,700, which is what we got up there. All right, let's prove another one. So here we have 5.987 times 10 to the negative 5th, which means the same as, moving to the left, 1, 2, 3, 4, 5 place values, decimal 0. But what does that mean? Well, switching pens here, that means 5.987 times, if I wanted to write that with a positive exponent, what would I write? Yeah, 1 over 10 to the 5th. Or I could say 5.987 times 1 over 10 times 10 times 10 times 10 times 10. Or 5.987 times 1 over, what did we say this was? Yeah, 100,000. Well, here's a fancy thing here. This is 987 tens, hundreds, thousands. So this would be 5 and 987,000. So we would write this 0.5987 over 1,000. If we had to convert this to a decimal, right? 1,000 goes into 5,987 5.987 times. And we're still multiplying it by 100,000. Well, for multiplication, we multiply across the top, 5,987, and across the bottom. 1,000 times 100,000, count up the zeros, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, and this would be 5,987 100 millionths. What would that look like? Well, 5,987. Let's see what it would look like if we counted it out up here. Tens, hundreds, thousands, 10,000s, 100,000s, millionths, 10 millions, 100 millions, which is what we said there. So this got a little dicey in there, but it's, increasing your number sense. Knowing how to manipulate powers of 10 is really helpful. Okay, so here are some sample questions that you may see on a future PARCC test. They, let's see, are maybe hard to see on the video. Okay, it says, the figure shows a spreadsheet Shana made to record the mass in grams of several samples of cells. Her spreadsheet automatically converts the masses into scientific notation. List the 4 samples from least mass to greatest mass. And you might think, ugh, I don't want to convert all those numbers. But do you actually have to convert those numbers? No. Which is going to be the smallest one? The one with the smallest exponent, right? So it would go this one first, so sample C. This one comes next, so sample B. Uh-oh, now it's a 5 and 5. Well, which one is smaller? Now remember, we're thinking of decimals, not negative numbers, right? So then the 6.13, and then finally the A. Now, could you convert all of those into decimals and do it that way? You absolutely could, but I'm a fan of making things not harder than they need to be. All right, let's try another one. Peter determined the area in square miles of a piece of land using his calculator. The result of his calculation is displayed on his calculator in scientific notation 7.4e-4. And poor Peter is probably wondering, what does that mean? And it says, which statement is true about the area of the piece of land? Could you please write what that means in scientific notation? Did you write 7.4 times 10 to the negative 4th power? Okay. Could you please convert that to standard form? Did you write 0.00074? Because the decimal is here. 1, 2, 3, 4. Okay. And so we have to see, what is it between? Is it between? No, not that. We have 1, 2, 3, 4, 5 place values. Which one of these can accommodate 5 place values? There's 4 and 3. 1, 2, 3, 4, 5 place values and 4. That must be the one. So we're just counting the number of place values that there are. That's all it is. Okay, I believe there's one more. Oh, 2 more. I'm sorry. 2 more for us to do. And then we have some opportunities for practice. Okay. It says, Lori entered the mass in kilograms of 4 substances into a spreadsheet. Her spreadsheet automatically converted the masses into scientific notation. This sounds very familiar, doesn't it? Which shows the 4 substances in order from least mass to greatest mass. You know what? Can you do this one on your own? We just did this. Please take a moment and do that yourself. Okay, this one would be the smallest one because it has a -5. -5 is smaller than all of these. Then this guy. Oh, wait, but there's 2 4s, right? So if there's 2 negative 4s, which one of these is smaller? 2.45. So, oh, that was 1, 2, 3, 4. So it goes C, A, D, B. C, A, D, B. C. Cool. Now we have one more. I was so excited. I thought we were done, but nope. Okay. A student uses a calculator. All these students are using calculators to estimate the number of leaves in a forest. Okay, I just gotta stop. Sorry. We were supposed to be doing real life situations. Sorry, this catches me as funny. Okay, I'm gonna be honest with you. I'm almost 40 years old, and I've never had to calculate the number of leaves in a forest. But I'm sure there's a good reason for this. Sorry, I'm gonna have to stop and get myself together. I just think that's funny. Okay, get it together, Rose. The student's calculation is based on an estimation of about 2 times 10 to the 5th power leaves on a mature tree. After the student performs some calculations, the calculator displays the result of 2 times 10 to the negative 8th power. Okay, let's read these different options here. So this student's result is 2 times 10 to the negative 8th power for all the leaves in a forest. That's kind of weird. Do you see a problem there? In a whole forest, isn't a negative 8 a decimal? So you're going to tell me 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. That there are 10,000, 100,000. There are 200 millionths of a leaf in a whole forest. I think the student needs to get out of the forest and not do this because their calculations are goofy. Let's look at this. It says the result indicates an estimated emission of 200 million leaves. That's not a thing. They went the wrong way. They went with a positive 8, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, not it. Nope. The result indicates an estimate of 2 to the 8th, but it doesn't. Goodbye. The result indicates an estimate of this. Yes, we agree with that. This is not reasonable result because it indicates that the estimated number of leaves is less than 1. You sound good, my friend. But let's check the last one. This is so silly. The result indicates an estimate of negative 16. Where did they get negative 16, guys? Do you see it? 2 times negative 8. No. This is not a reasonable result because there cannot be negative number of leaves in the forest. No. Wow. That was super special. Okay, well, I'm glad we spent our time on that. Right. Super fun. You know what? I don't mind actually studying other people's silly mistakes. It forces us to think critically about why things are wrong. But that was silly. Seriously? Okay. Anyway. So you have some opportunities to practice what you have just learned. This is one of those things that's not too hard of a skill. You just need some practice. So here's the homework. You are to complete all of it. The top half, you should convert the numbers in standard form to scientific notation. Here's a spoiler alert. If you compare that to your notes, do you have examples that you can use? 2.578. Oh, we did one like that. Did we do a very long decimal like that? Yep, we did one of those. Did we do one like this where there's a 0 there? Oh, we did one like that. Good. Like this one? Yeah, that's like that one. So the point is if you have been taking good notes, like this one goes with this one, you basically have the answer written down for you. Samples that you can use to help you navigate this thing. So your challenge for the rest of class, you should have some time, is to fill in as many of these as possible. Please do not get sloppy and rush through and make silly mistakes. If any of this goes poorly, if you're having a hard time with it, of course, I will be back in class tomorrow, and I'm happy to answer any of the questions that you have. So, yeah. Thanks, guys, and I'll catch you when I'm back. Bye.